Okay, welcome back, students. Let's cover 1.4. Okay, 1.4 is on separable differential equations. Okay. By definition, a first order differential equation is called separable if it can be written in the form P of y dy dx is equal to q of x. Okay, so we have some function of y times the first derivative, y prime, is equal to some function of x. If we can write it in this form, it's called separable. We get all the y's on one side, we get all the x's on the other side. Okay, theorem. If py and qx are continuous, then py dy dx equals q of x has a general solution integral of py dy is equal to integral q x dx plus c. Okay, let's do an example for one. Solve y prime is equal to negative 2xy squared. Okay. Okay, I want all the values of x on one side, all the values of y on the other side. So what I'm going to do is I'm going to divide by y squared. I'm going to leave the negative on the right side. I'm going to let that be the part of the function of x, and we're going to have divide by y squared. So I get 1 over y squared y prime is equal to 2 negative 2x. Okay, and I'm going to change this y prime into a dy dx. So 1 over y squared dy dx equals negative 2x. And now I'm going to multiply both sides by dx. I'm not taking the derivative of both sides. I'm just multiplying by the dx. Okay, 1 over y squared times dy is equal to negative 2x dx. And now that's been separated. Okay, that's called a separable equation. Now what I want to do is I want to integrate. I'm going to let this y be y to the negative 2 dy. Let's integrate both sides. Integrate negative 2 dx. Okay, we're going to integrate with respect to y on the left side. So this is going to be y to the negative 1 over negative 1 dy. Or sorry, not dy. Okay, and we could put a plus c there except it's going to be combined with the other plus c. And so we really only need one plus c. Okay. So that's why in the theorem, we only end up with one plus c. Okay. So that's the plus c that we end up with. Okay. So the constants will combine at the very end to just leave me with one value, one constant value. Okay, this is going to be equal to integrate this, we get negative x squared. Okay, and then we'll do plus c. Okay. So this becomes negative 1 over y is equal to negative x squared plus c. Okay, and then the negative I can multiply through by the negative 1. And I get 1 over y is equal to x squared minus c. I might keep the minus. I could turn it to a plus if I wanted to. It really doesn't matter. Okay, and then I want to solve for y. I can look at this as x squared minus 1 over 1 and then flip everything upside down. And we get y over 1 is equal to 1 over x squared minus c. And anything divided by 1 is itself. And so we just get that guy there. Okay, that was the solution to the differential equation. Okay, let's go over the next example. Number two is solve dy dx equals negative 2xy. Okay, this now has a y and not a y squared like we saw in the last problem. Okay, solve dy dx equals negative 2xy for y equals, or y is not is equal to 1. Okay, so this is an initial value problem. Okay, we have an initial value. Okay. And so we're going to get a particular solution. So the first thing we need to do is find what the general solution is. Okay. So let's look at the general solution. So we have, let's separate this. Okay, dy dx is equal to negative 2xy. Divide by the y. Divide by the y. We're going to get 1 over y dy dx is equal to negative 2x. Multiply it through by the dx. And we get 1 over y dy is equal to negative 2x dx. Now we're going to want to integrate both sides. The integral of 1 over y is natural log y, absolute value of y. Okay, this again is going to give me negative x squared plus c. And I'm going to call this C1 because the next step I want to raise both sides to the base e. Okay, and that's going to cancel the natural log. So I end up with absolute value y is equal to e to the negative x squared plus c1, but I'm going to let that be multiplied e to the c1, and e to the c1 I'm going to let be c2. Okay. Let e to the c1 equals c2. That'll be my constant. Okay. because e to a constant is just a constant, just another constant. Okay. So now we have absolute value of y is equal to c2 e to the negative x squared. Okay. So because of this absolute value, we're going to define C3 in a couple of different ways. Okay. If C2 is positive, then let C3 just be C3. If C2 is positive, it doesn't matter what the absolute value is. Okay. If they're both positive, then we don't have an issue. So I'm going to say let C3 equal C2 if y is greater than 0. Okay, just let C3 equal C2, whatever that is. Okay, but if C2 is negative, I'm gonna change that to a positive value. If y ends up being a negative value. Okay, if y is less than 0, then I'm gonna flip signs and I'm gonna let that be a negative C2. Okay, thus, regardless of what I have, y is going to be equal to C3 times e to the negative x squared, regardless of the sign of C2 or the value of the function after, setting it equal to the absolute value of that. Okay, the absolute value, if I were to solve that, would give me a positive and a negative. Okay, depending upon different conditions. Okay, so we kind of take care of that condition. Thus, the appropriate sign for C3 will be determined by the initial conditions. Okay, so here's my general solution. Okay, and so the if we plug in a particular initial condition, okay, initial value problem, and we let y not equal 1, okay, then what's c going to be? Well, let's see what we can get here. I'm going to say that y equals c3 e to the negative x squared. 1 is equal to c3 e to the negative 0 squared. Okay, so plugging that in. Okay, e to the 0 is just 1. So divide both sides by 1. Okay, and we get c3 is equal to 1. So my particular solution is y equals 1 times e to the negative x squared. So that's just e to the negative x squared. Let's see how this would contrast if I had a different initial condition. Okay. Okay, if I will say, but if y not equal negative 1, then what would be the initial condition is going to dictate what C3 is. So if it was negative 1, then we would get negative 1 is equal to C3e to the negative 0 squared. This again, e to the 0, that just goes to 1. And so C3 is equal to negative 1. And so I would get a different curve in the family. I would get negative 1 times e, or negative e to the x squared. E to the negative x squared. So that would give me a different, right? So, and that kind of makes sense because what's the y value at 0? Isn't that, when x is 0, isn't that just the y-intercept? Isn't it we're just changing the y-intercept from 0, 1 to 0, negative 1? And so we're forcing it down, the function down, this e to the negative x squared function. Aren't we just forcing that down? Okay, and so, yeah, so it would make sense that, it would be, have a different value on that parent function. Okay. And number 3. Okay, a hot metal bar whose temperature is 350 degrees Fahrenheit. It's placed in a room of 70 degrees Fahrenheit. And after 2 hours, or sorry, not 2 hours, after 2 minutes, minutes, the bar is, the temperature, the bar is 210 degrees Fahrenheit. They use Newton's law of cooling to determine the temperature of the bar after 4 minutes. So we need to know what's the equation for the differential equation for Newton's law of cooling. Okay, and we saw that in I think it was 1.1, section 1.1. We said, hey, here's the dt. The temperature is a function of negative k times T minus Tm, and Tm was the ambient or environmental temperature. Okay, so let's see if we can solve this by using a separable differential equation. Let's put everything that involves a capital T on one side and everything that involves a lowercase t on the other side. Well, there are no lowercase t's in my function, so I am going to just multiply both sides by dt. Okay, and that becomes d capital T, d lowercase t. dt is negative k times t minus tm, k dt. And then I'm going to divide by t minus tm. Okay, keeping in mind that tm is a constant. We have to think of tm. Okay, or we could say that it behaves like a constant, so just keep that in mind. Okay, Tm is a constant. Okay, because the environmental temperature doesn't change. Okay. And so we get 1 over T minus Tm is equal to negative k dt. Okay, so that's what I'm going to be working with. Okay. Okay, so now dt, sorry, d capital T. So now we want to integrate this guy. Okay, maybe I'll give myself some extra space here. 1 over t minus tm d capital T. Sorry, the t's can get a little confusing here. Okay, my integral of negative k dt, lowercase t. Okay, so now, what does this behave like? 1 over t minus tm. Well, I could do a u sub on that. U is equal to t minus tm. And if I were to do du is equal to what? Well, this becomes dt. Okay, because this minus tm, that just becomes 0. That goes to 0. T, the derivative of t is just dt. And the derivative of negative tm, again, that behaves like a constant. That just goes to 0. Okay, and so du is equal to dt. And so if we integrate 1 over u du, okay, what is that? That's just natural log again, natural log of u. But what was our u? Our u was t minus tm, so that's the natural log of t minus tm. Okay, capitals. So that's our left side. Now let's look at what our right side should be. Our right side, we're going to just integrate a negative k. Again, k behaves like a constant. Okay, and so negative kt plus c, okay, is that one. I'll put a c1. And so let's drop that down, negative kt plus c1, because we are going to let e be the base. That gives me t minus tm is equal to negative e to the negative kt. Okay, times e to the c1, and we're going to let e to the c1 be c2. Okay, so t minus tm is equal to c2 e to the negative kt. And we're going to do kind of the trick that we did the last time. Okay, we can turn that c2 into a c3 and just say that c3 is, you know, it's a constant, and it can just flip signs. If it's negative, it's positive. It's positive, it's negative. And so we can really get rid of the absolute value bars by just changing that c2 into a c3. So, oops. So let's do that. Let's so t minus tm is equal to c3 e to the negative kt. And I can just generalize the c3, and I can toss tm to the other side. So t is equal to tm plus c e to the negative kt. So that's just some general constant c, and some general constant k, and some general constant, some ambient temperature of tm. So that we solved for our differential equation. So that's nice. So this is basically Newton's law of cooling solved. Okay, and so we have a nice, concise formula there. Okay, and so we do have some initial conditions, right? What are initial conditions? Well, Tm was equal to hot metal bar whose temperature is 350. That's at time 0. Okay. So TM, what was TM? TM was place in room of 70. So TM is 70 degrees. Okay. So T is equal to 70 degrees plus C e to the negative KT. Okay. Okay. And we want to know, well, what was the temperature at time 0? Okay, when little t is 0, then what was the temperature? Well, basically T naught, or T at time 0 is equal to 70 degrees plus C times e to the negative K at 0. Okay, and we said that temperature, okay, was T naught was equal to, I think it started out at 350 degrees, right? Yeah, 3, and then it went to 210, 2 minutes later. Okay, so this went to 210. Okay. Or maybe that's what we're looking for. Yeah, no, that's fine. Okay, so T naught was 350. And that equals 70 plus C. Okay, C e to the 0, okay, which is 1. And so if I subtract off 70, I get 280 is equal to C. Okay, so that's nice. So for this particular scenario, we get T equals 70 degrees plus 280 times e to the negative KT. Okay, so that's for this particular scenario. Now, I still don't have, so this is basically a particular solution. However, I don't know what K is. So I need a little bit more information about K. Okay, and so that comes from our next piece of information that tells me that after 2 minutes at T of 2, we get this temperature to be 210 degrees. Okay, so that's 210 degrees is equal to 70 degrees plus 280 e to the negative 2k. Okay, subtract off 70, we get 140 equals 280 e to the negative k. Divide by 280, we get 1/2 is equal to e to the negative 2k. Okay, I might change that 1/2 to a 0.5 because I'm going to take the natural log of both sides now. Natural log of 0.5 is equal to negative 2k. Okay. And so, well, maybe I won't change it to net 0.5. What I'm going to do is I'm going to change this 1/2 to 2 to the negative first power. You'll see why I do that in a second. I'm just kind of setting it up because I have this negative here, and if I divide by that negative 2, okay, I get the natural log of 2 to the negative first power, okay, divided by negative 2, or negative 1/2, multiplied by times negative 1/2. Okay, and what I really want to do is just take this negative 1 and you know, put it in front. I'll put it in front like this so you can see. I don't know how adept you are at the logarithms, but if we do that, then we can raise this 2 to the negative first power to another negative first power. This goes up here. Okay. So this is 2 to the negative first to the negative first. Okay, which this is just 1/2. Flip that upside down, or these negative ones, when I take a power to a power, those are gonna cancel. And so I'll just left with natural log of 2/2 is equal to k. So that's a little bit maybe nicer of a form. Okay, so now what do we have? We have finally our particular solution. Okay, our particular solution of what? We have t equals Tm, which was 350, or sorry, not 350, 70, plus C, which was 280, e to the negative natural log 2/2 t. Okay. Okay, I'm seeing if I want to do anything more with that at this point. I think we're okay. Yeah. Okay, so now it's saying, well, what is the temperature after 4 minutes? So will this equation give me the temperature of the bar after 4 minutes? So I just want to take this value and I want to plug in for t equals 4. Okay, so 70 plus 280 e to the negative natural log of 2/2 times t of 4. Okay. So now let's simplify this. This becomes 70 plus 280 e. This negative 4, this negative and 4 are going to cancel with this 2, leaving me with a -2 natural log of 2. Again, I can make this the exponent now. Okay. And so this becomes 70 plus 280 e to the natural log of 2 to the -2 power. That is going to cancel. And we're just left with 70 plus 280. And then this 2 to the -2 power, that's just 1/2 squared, which is 1/4. And so I get 280 divided by 4, which is 70. And so this is 140 degrees after 4 minutes. So after 4 minutes, basically the bar went from 350 degrees to 140 degrees. Okay, after 4 minutes, the temperature of the bar is 140 degrees. Okay, using differential equations and Newton's law of cooling. Okay, let's do one last example for this section. Okay, number 4. Solve y prime equals 9x e to the 3x over e to the y plus 4y squared. Okay, so nice separable differential equation because everything that involves x is on the top and everything that involves y is on the bottom. So basically, I'm just going to want to cross multiply in a way. Okay, so let's just cross multiply there. I'm going to get EY plus 4y squared dy is equal to 9x e to the 3x dx. Okay. So let's integrate both sides. Okay. This is fairly straightforward. On the left side. Okay. Okay, so the integral of e to the y is just e to the y. The integral of 4y squared is just 4/3 y cubed. Okay, we'll leave our plus c for the other side. Okay, the right side is actually integration by parts. Okay, remember Liate. Okay, logs, inverse trig. Okay, algebra, and then trig, and then exponentials. Okay, and that's for the order for u. Okay, so let's kind of take a pause here, and we're going to do u equals. Okay, we have an exponential and algebraic, so I'm going to use the algebraic first. Okay, for u. Okay, and then dv is going to be e to the 3x dx. Integrate that, I get 1/3 e to the 3x. Take the derivative of u, and I get 9 dx. Okay, and then I just crisscross applesauce. uv v du. Okay, so I say that uv is 9x times 1/3 e to the 3x minus the integral of 9 times 1/3 e to the 3x dx. Okay, so let's integrate that. There's y cubed, so we have our two sides. Okay, and so this is going to be the 9 and the 3 cancel to leave me a 3, so that's 3x e to the 3x. Okay, minus, this is again going to cancel, leave me with a 3. That's just going to, the integral of 3 e to the 3x is just another 1/3 e to the 3x. So this is minus 3 times 1/3 e to the 3x. Again, that's going to cancel. And so we're left with 3x e to the 3x minus e to the 3x. Okay, plus c, some plus c. I probably should have put that in the previous line. But then we get our plus c. So e to the y plus 4/3 y cubed equals 3x e to the 3x minus e. Now I could factor out the e to the 3x if I really wanted to. Maybe make that a little bit simpler, simplify. And we get e to the 3x times 3x minus 1 plus c. Okay. Okay, and that's section 1.4. And I'll see you guys in the next one.